Thank you very much, ladies and gentlemen, and we'll begin. We'll have to make this a fairly tight press conference because Rolf-Dieter Hoyer of CERN actually has to leave this afternoon and is due to give a television interview. So I'll bring the press conference to a close quite suddenly after 45 minutes. I don't need to tell you that this is big science and big data in person. We have the Director General of CERN and we have the leader of the Atlas team. Yes, I'm sorry. Yes, and the co-discoverers, as it were, of the Higgs boson before us, and they want to talk to you about the startup. And I can tell you that there is a press release at the back of the room. There are plenty of copies, so you'll have time to pick one up later. That will outline some of the detail of what they have to say. And Dr. Hoyer.
Yeah, thank you. Well, we had 3 years of running with the LHC. 3 very, very successful years. And it's obvious that after 3 years of running such a machine needs also a break. And not only the machine itself, but all the other machines at CERN, which are the pre-injectors to the LHC. So this is why we are still in the shutdown at the moment. And the shutdown was supposed to take 2 years. Within 1 day, we are on schedule, so that's fantastic. We are now 3/4 through the shutdown, yeah, roughly 3/4. It's fantastic. But why did we need 2 years? Because we had to open the whole machine roughly every 20 meters over the 27 kilometers, which in order to do something, in particular to reinforce the interconnects between the magnets, and this is obvious that this takes a long time. We are restarting already the injectors. That means the smaller accelerators have already seen the first beam again. So the small experiments which are situated at these accelerators, they will get beam and therefore physics soon. The LHC is supposed to restart in January with seeing its first particles. Now physics, I hope, can restart around Easter also. And I say Easter because I don't know when Easter is next year. It's around Easter next year that we hopefully get the first data. And then we assume a roughly 3 years running period again for the LHC before it gets its other next big shutdown. And altogether, we foresee at the moment a 20 years additional program at the LHC. So if you take it time-wise, we have taken 3 out of, let's say, 25 years, so that's a 10% time-wise running. But if you look at the amount of collisions which we produce, we have only 1% of collisions up to now collected. So we want to get a factor 100 more until 2035, because there's a huge amount of physics to be done. Discovering the Higgs boson is easy. That's at least what I told them once they have discovered it. The work starts now, and I think the work on the Higgs boson and what else is beyond it, all the fascinating physics which we are looking forward to, I think I leave to the particle physicist. Fabiola.
Thank you. So following up on what the DG said, clearly the discovery of the Higgs boson was an arrival point in the sense that it awarded the work to more than 20 years competent and dedicated work of the international community, but at the same time is a starting point. So with the higher energy at the LHC starting on Easter 2015, almost a factor of 2 larger, a bit less than a factor of 2 larger than what we have today, many opportunities open. Actually, we have several certitudes, I will say, that gives us hope that we can really have a very exciting physics program. The first certitude is the Higgs boson itself. It's a new particle. And at the moment, we don't know it as well as we know the other elementary particles like the W and the Z boson, the top quark. And as it happens with a new friend, you want to know him or her. I don't know if you should say him or her for the Higgs boson, perhaps it, no. You want to know him or her better. And so we are going to measure it in all details, to do a complete scanning, complete identikit of this particle, not only because it's our duty to know it better, it's such a special particle, so different from all other particles we have discovered so far, but also because it's a door to new physics, because new physics, which is needed to address many open questions about matter and the universe, may well affect the way the Higgs boson interacts with the other particles. So this is one of our first goals. And the other goals are the other goals for which the LHC has been built, conceived and built, not only to discover the Higgs boson, or better to understand the origin of the particle masses, but also to address many open questions that are still there, big question marks, big mysteries, like why the universe is made mainly of matter with very little antimatter. What is the particle that constitutes the dark matter? Why is the Higgs boson itself so light? And so we know that these questions are there, and we know that we need new physics to address them. The problem is, where is this new physics? Is this at the energy scale that the LHC will explore starting in 2015? Or is the higher energy scale, which will call for future machines? Anyway, we have the duty and the right and the excitement to use the LHC, which is the most powerful accelerator we have in our hands today, in the best possible way, and exploring its ultimate performance. And this will take time, will take 20 years, because of course it requires a lot of data. There are some phenomena, like the deviations of the new physics will produce to the interaction of the Higgs boson with other particles, that require a lot of data because they are tiny. So I think I will stop here, not to abuse of the time.
Thank you very much. Let me introduce myself very briefly. My name is Tim Radford, and I'm going to be your friendly neighbourhood moderator for the duration. It will take questions, but I would ask you please to just wait for a microphone to turn up magically before you, because this is all being recorded, and we want to know who you are and what organ you represent. Does anyone have a question? Yes, one there.
Hi, I was wondering if you could give me some more specifics of what you're interested in learning about the Higgs boson. So you said you want to know it better. What kind of things do you want to know?
So what we are going to do is to measure the way the Higgs boson interacts with the other particles. So the way it decays, it disintegrates itself, it produces, and then it disintegrates itself immediately, and it decays into pairs of Z boson, W boson. Recently, as you perhaps have learned from a press release this morning, we also observe interactions with the Higgs boson with fermions, so with the matter particles, so-called matter particles. Now, at the moment, we have measured this interaction at the level of typically 20% experimental uncertainty. But to detect deviations coming from new physics sitting perhaps at a very high energy scale, we need to reach a precision at the level of few per mil to the percent level. Okay? So this is what we are going to do in the next years, many years.
Thank you very much. Question right down there, and then one here.
Maybe to add to that, we have clear predictions how the Higgs boson should behave with respect to all the other known particles. And any deviation from this expectation is what Fabiola says, and that would then be coming from the influence of other particles, for example, dark matter particles. That's the point.
Right, questions. And do say who you are.
Yes, I'm Corina Negra from Radio Romania, and I have two very short questions. The first one is related to Romania, and I apologize, but I don't have a chance to interview you, Professor Hoyer. So my first question would be, what about Romania's accession as a full member state? And the second question is related to a press release released by CERN that we got today. It is, and I will quote, in a paper published in the journal Nature Physics today, the CMS experiment at CERN reports new results on an important property of the Higgs particle. What are these new properties? Thank you.
I take Romania, and Fabiola takes the properties. I was recently in Bucharest talking to your government representatives, and we have a clear indication that Romania is absolutely interested in becoming a full member next year. So it will happen in the course of next year, most probably towards the end of next year. We have found a mutual agreement how to do it.
Thank you.
So concerning the new properties, until now we have observed with very high significance and measured in details the way the Higgs boson interacts with what we call the force carriers. Force carriers are the particles like the photons, the W, the Z boson, that are responsible for transmitting the elementary forces at macroscopic level. So this has been quite well measured. More difficult to measure is the way the Higgs boson interacts with so-called fermions, like the quarks and the leptons. And so now we have actually observed with very good significance and very good confidence the way the Higgs boson decays or interacts with two types of quark and leptons, the bottom quark and the tau lepton. And so this is what the press release is about. This is yet another important step in the understanding of the behavior of this particle, and as far as we can tell today, with the precision we have, it behaves very much as a standard model Higgs, but as we mentioned before, the impact of new physics, new particles, very heavy physics, really is on very tiny deviations. So today we don't have yet the experimental precision to test at that level.
Questioner there, and then here.
Frank Grotelüschen for German National Radio. Question to Rolf Heuer. So you said that LHC will start in early 2015 again. And what do you think when it will reach its design energy, this 14 DeV, and its design luminosity?
Unfortunately, I left my crystal ball in my office. Why are we going to 13 TeV and not to 14 TeV, which is the design energy? The reason is that some of the magnets, which are very well behaving, except that they have some of them have Alzheimer. But it can be cured. So they forgot that they all have been trained up to 14 TeV equivalent. We know that with very few quenches, we will reach 13 TeV. Now, not everybody knows what a quench is. If you have a superconducting magnet, you make it cold, and then you start ramping up the current, and at a certain moment, there are some surface impurities, and therefore the superconducting behavior of the magnet gets away, and it becomes normal conducting, so you immediately have to switch off in order not to boil the helium. And so you go on like this, so this impurity has been burned away, and so you go, with each step you go higher. And we know that very few of these quenches we will reach 13 TeV equivalent. Now each quench of this type shakes the machine, and this is a mechanical stress, so we don't want to overstress the machine, and therefore we will stop at 13 TeV equivalent. After some experience, we will slowly go up to 14, which takes many more quenches. But we prefer, after 2 years of shutdown, to give the scientists again data and go later a little bit to 14 TeV. I would think that it depends now also what we find at the very beginning, how well the machine is running. It's essentially, so to speak, a new machine once you had opened it every 20 meters and redone the connections. It depends a little bit on the behavior of the machine. If you go up after a few months or after a year or so, but I think that the experimentalists want to have, for a certain time, stable situation. So I personally would also prefer to be stable in energy for quite some time. Yeah, I think that's much better. Design luminosity we will reach, I think, very quickly. The machine has behaved extremely well in the first 3 years, going beyond the design luminosity if you scale it down by energy. So I would assume that the same will happen at 13 TeV. So design luminosity, I think, should be reached very quickly.
Thank you very much. Questioner here and then there. And by the way, although our speakers have to go, there are 3 physicists from CERN at the back of the room who would be delighted to answer any further questions. This could run and run. Sorry. Yeah.
Popular Science Magazine Terra, a question to Fabiola Gianotti. Could you please say something about this possible metastability of Higgs boson and its implications to our universe?
So yes, well, again, also my crystal ball is in my office, and I must say, so the question is that the mass of the Higgs boson, I was mentioning before, we don't understand exactly why it's so light, and combined to the mass of the top quark, which is also a very interesting particle because it's so heavy, so much heavier than the other particles, are such that it seems that our universe is not in a situation of stable vacuum, but metastable vacuum. What means metastable? That on a time scale of ages of the universe, not tomorrow, don't worry, tomorrow we are still be around, may transit from the present state to another vacuum state. Now, these are possibilities that are based on theoretical calculation that have some uncertainties, but also depend very much on the precise knowledge of the mass of the Higgs boson and the top quark. And that's why we are going with the LHC and high luminosity LHC to measure the Higgs mass and the top quark mass with the highest possible precision, a few per mil for the Higgs boson at the level of also alpha % for the top quark. But this way may need also future collider and future accelerator to measure the top mass at the level of 10 MeV or so, and so to restrict the error bars. But again, to encourage you, no problems for tomorrow. The day after tomorrow. The whole week should be okay, so ease of is safe.
Next question. Once again, name and...
Yes. Tiit Candler, Estonia, freelance and science writer. Dr. Heyer, I'm interested in a little totem experiment. Will you continue it or will you shut it down?
It continues. But it continues, for those who don't know, the LHC does not only have the CMS and Atlas, the two biggest experiments, it also has two big experiments, that's ALICE and LHCb, and it has 3 small experiments. One of them is Totem, and Totem is very closely related to the CMS experiment. Yes, it will continue because it does very interesting physics. Totem does the physics in the very far forward direction. Yeah? The other experiments cover mainly the central region, also of course going forward, but not as far forward as the Totem one. And so you can study some special processes there, and it continues. Yes.
Clive. There's a mic coming.
Clive Cookson from the Financial Times. Yesterday, Rolf, you said that a clear vision had emerged.
Between the regions.
Between the regions, a very clear vision of the future. Yeah. For the first time, we have a global vision of the field. Can you tell us what that vision is, please?
First of all, the vision is that the different regions want to work together and not duplicating things in the different regions, which is very important given the scale of the projects. And of course, I'm talking essentially about the large-scale projects. So all 3 regions, I mean, with regions, I mean Europe, the Americas, and in particular Japan. But the rest of Asia is more or less buying into that, as far as I can see. So the LHC and its high luminosity upgrade, that means the running until 2035 is high priority or highest priority and essentially in all the regions. So this is already very good. So they look beyond their regional boundaries, as does the European strategy. It looks beyond the boundaries. So we are looking forward to receive, for example, from the east, to receive from the east proposal how to implement the linear collider in Japan. And we are in very close connection with our US colleagues to work together on a collaboration in the West on the neutrino experiments. So Europe is looking beyond its boundaries, participating in the other regions in an official way, not only on individual group basis, but really in an official way. The US is looking in an official way to collaborate with us, and Japan the same. And so the priorities are more or less the same in the 3 regions. And I think this is for the first time officially stated in the different papers. And I think this is, since a long time, needed to show that we can work globally, because the next project must be a global one. And so I'm very happy that it sees some shape.
Wait for the microphone.
Yes, Corina Negra, Radio Romania. So the next project you see, I mean, from the 2024 onwards, that huge circle, 100-kilometer circle, would be in this, how to say, in this manner. I mean, it will be an international collaboration more than previous ones.
Yes, but on the second part of your question, it's an absolute yes. It has to be a global project. On the first part of your question, it's a no, because it will not start 2024. The point is 2024, the Halloumi LHC will start. So we are still in the LHC era. However, the first physics discussion and discussing on how to do physics at the LHC started 30 years ago, 1984. So this was already a timescale of 30 years. So now it's time to begin a study, not a project, to begin a study what could be the next larger circular collider, how to build it, because at the time, again, to take the analogy to the LHC, the magnets which are today in the tunnel of the LHC, they did not exist 1984. It took roughly, don't take it too seriously, but canonical 10 years to do R&D on the magnets, 10 years to build the things and then to install it. So this makes this large timescale, and this timescale will repeat again, even on a bit more, even on a more stretched timescale. So we are beginning a study to see how feasible it is. Tunnel is easy. Switzerland knows how to dig a tunnel of 80 or 100 kilometers. That's no problem. The problem is what goes inside the tunnel. And the other point is that we have to see from the LHC and from other experiments all around the world which direction physics tells us to go, because you need to have a clear case in order to present that. But it's without any doubt it has to be a global project, much more global than the LHC is already a quasi-global project, but not as global as the next project has to be.
Thank you very much. Questioner here.
Ana Mateu from magazine Méthode from Spain. We're very interested in social perception of Higgs boson and how media covered the announcement of the Higgs boson. We detected that most of media used the nickname the God of Particle, and I would like to know what do you think of the use of this nickname, if it's a positive or negative to disseminate the research. Thank you.
I mean, I can say I don't like it, but I have accepted it, but the rest can come from Fabiola.
Yeah, I don't like it either. As you know the story of the name, it's the name that an editor of the famous book written by Leo Liederman, a Nobel Prize, wrote about the Higgs boson, and the editor changed the name, and the original name was not so nice, but the editor decided to change the name, the title, in order to sell it more. Okay, so we don't like.
Well, you can tell them it was supposed to be called the goddamn particle.
Exactly. So and so the editor thought that the God particle would be more attractive for the public. Now, of course, we don't like it, but in some sense, because it's not justified, but in some sense, what it indicates is that something in that message is that this, which is true, is that this particle is a special one. As I said before, until the 4th of July 2012, we had discovered 16 elementary particles. The Higgs boson is number 17. Okay, and it's completely different from all the others. It has a completely different role. It has completely different fingerprints and properties. Okay, so in that sense, it's a special particle. But I don't like either this particle.
Questioner there. Just hang on for the mic.
Good morning. My name is Mónica Salomone. I am freelance for Spain. You have both stated several times that you have left your crystal ball at home or in your office, but at the same time you are talking about planning for a very global project for the very far future. What happens if you start planning now and the physics in between, the results you get from the next decades operating the LHC change so much. I mean, you don't know anything about, apparently you don't know really anything about dark energy, dark matter, and you are going to search for particles in that direction, or for physics in that direction, and even for new physics. So my question is, how can you plan for a project very global, very far away in the future, when you don't really know nothing about what's going to happen in the next decades?
We are not planning into one direction only, we are planning in different directions. For example, the future circular collider, which would be at the energy frontier with collisions between protons. Instead of going to 14 TeV, it would hopefully reach 100 TeV, plus or minus something. I mean, 100 is just a round number. I agree, we don't know if that is sufficient. This is why we are also looking into a linear collider, where we look onto similar questions, but with a different angle of addressing the... If you look onto certain questions only from one viewpoint, you have, so to speak, a two-dimensional picture. If you look from the other angle, then you suddenly have a three-dimensional picture. This is why you need to have complementary instruments in order to do that. Astronomy does the same, it looks at the similar questions with different instruments. So it's very important to look also with a different instrument. That would be a linear collider. We are also having our foot in the door on the neutrino physics together with the Americans. So we go into all these different directions. But planning means doing a study, and at the same time, at this study, preparing the political steps in order to get a global project together. And if you have put down the means to have a global project in one direction, then it's much easier to put down a global project, to pin down a global project in another direction. So then you have already cleared the landscape there. So we go into different directions. In addition, we are keeping the diversity at CERN, diversity in one respect as you addressed it yesterday, but also diversity in terms of physics questions. We keep that very strong. We have upgraded all our facilities for intensity frontier, for intensity physics or low energy physics, nuclear physics. We have upgraded all of our facilities there for the next, I would say, 10, 20 years. They are very competitive. We have, for example, the only facility in the world which can produce anti-hydrogen. I was recently at the Vatican to assure the Pope that this is not of any danger to the Vatican. But it's the only facility which can study, can produce anti-hydrogen, can study it, and that addresses also the question of the matter-dominated universe, similar to some of the experiments at the LHC. So we are looking into several directions in order to put the project on the table once we know where to go.
Questioner here, sorry, questioner there and then here. There.
I guess it's a follow-up.
Yeah.
Ljubica Urošević, TV Metropolis, Serbia, Belgrade. You have mentioned yesterday a fascinating fact that more than half of your researchers are age under 35. It is really fantastic. But how many, speaking about diversity, how many research centers or laboratories are included until now in the project?
So I can say about the experiment, they are very similar, but at the Atlas experiment in particular, we have 177 institutions, university, laboratories from 38 countries from all over the world, from South Africa to China to Australia to Southern and Northern America, Europe, everywhere. And I think at CERN there are more than 60 nationalities, right? Am I right, Dr. Jenner?
Many more.
Many more.
Okay, at CERN we have 98 nationalities registered to do science. We have collaboration agreements with between 70 and 80 countries. I don't know the exact number. And I think altogether we have agreements with more than 400. James, how many do you remember? No, he doesn't remember. Okay, more than 400 institutions all over the world. Because there are also many small experiments which, of course, have many different institutions. And we are trying to enlarge this, and we see a lot of interest also in other programs beside the pure particle physics programs.
Thank you. The question coming up again.
It is indeed a follow-up, but not scientific. I just wanted to know, what did the Pope say?
Well, my remark was more a jokey one. He was very interested in the philosophical debate between philosophy, theology, and science together, and we discussed a little bit the difficulty to find a common language. Because if we talk as a scientist about proof or truth, then our meaning, interpretation of this word is completely different to the meaning or interpretation by a philosopher or a theologist. And actually, in 2 hours, I should open a workshop close to CERN about philosophy and science. So I reopen it in the evening, then at dinner, where we exactly discuss this language problem, how to get analogies between philosophy, theology, and science, and how to come to a common understanding, for example, of the word truth. Because you can open a lot of these debates. The problem is if you don't have the basis that you understand what each other is saying with the different words, you talk not on aside you. Yeah? So you have to first make the basis. And that's quite interesting. I can tell you all religions want to be present at that workshop. That's encouraging.
Question here.
So my name is Prashant. I come from Bangalore, India. Work for a newspaper called Deccan Herald. Just want to know 2 things, sir. One is, are you preparing a second generation of leadership compared to what you have now to transfer knowledge to them so that it continues from generation to generation? That's one. Secondly, how has it impacted syllabus, for instance? How has CERN physics impacted syllabus in European education, maybe school, college, post-graduation?
The second question was on school and how we work together with schools and teachers, if I understood correctly. Impact of CERN on
education syllabus and
yes. If I take that question first, the first question I didn't get very well. That was how we transfer the management skills. Or
no.
Well, it all goes towards the question of capacity building. Well, first of all, I don't like the word capacity building, but I know it's a buzzword in politics. What is capacity building? It is getting people, young people, teachers, everybody acquainted with better education, better training, especially in science, technology, etc. So we have several programs here, and the one which is maybe the most efficient one is the teachers program. So we have around 1,000 teachers per year passing through workshops at CERN in their mother tongue. So they get the workshops in their mother tongue. That does not mean that they come only from one country. It can be a mix of different countries where their mother tongue is the same. Portuguese is a good example, or Spanish. German is a smaller example. Okay. They get presentations by scientists, that means physicists, engineers, etc. And they are supposed to network again then at home, and then it's continued by video courses, etc. So in that way, we hope that these teachers are getting remotivated and familiar with the modern questions of physics and how to address these questions. And that's a huge success. We are approached by different countries which want to connect with us exactly on this capacity building. So we are trying to promote that as much as we can. We have agreements now with some of the smaller countries in the Americas, in Asia, in order to do this teachers workshop. Can also mean that we do a teachers workshop in the country itself, but it should be mainly at CERN because we cannot invest too much of our resources into that. But I think it's something absolutely important to have this. And it would be nice if these teachers would be at some stage motivated and powerful enough to change the curriculum in physics, for example. I mean, if you start the curriculum at high school with the 18th century physics, you lose 99%. If you start talking to them on the big questions in physics nowadays, you lose less. And you can talk about these physics problems and physics questions of today without using mathematics at the beginning. For the solution, of course, you need mathematics. But in order to get people interested and staying in science, you can talk about it without any mathematical background or without much mathematical background. Then we have programs for school kids, which we started in the region of CERN. That means in the part of Switzerland, in the part of France where we are situated. And this program, which is, how is it called today? Slip in the, no, it's different. Oh yeah, in the skin of a researcher. And it's very interesting, and that now gets much beyond our region, so it's taken over in other countries. In a few weeks, no, in 1.5 weeks, I open a new school lab. It's called S'(Cool Lab. That means where the schools can make experiments. In a few more weeks, I open a new beamline. At one of our small accelerators, we have a dedicated beamline which we give for 2 weeks to school classes. And we had a competition for projects in schools, and we got 292 excellent proposals from all over the world. And these proposals are judged by scientists. So in the same review committee which judges the experiments of the scientists is also judging the experiment proposals from the school kids. And it was obviously a fantastic event, and the reaction of the school kids was, we have already learned so much, we don't in principle even care if we get the first prize or not. The first prize is performing the experiment at CERN. We have learned so much that this was already worth to participate. And for many of them, it was the first time they learned how to do a little bit of science. And I'm not absolutely familiar with all the details, but they were fantastic proposals. I hope some of my guys in the back, they know some of the proposals. So if you're interested, address to them, but not to me. So we have a lot of these programs.
Time for one last question, and then I really will have to bring this to a close because Rolf has to get to a plane. Okay.
So you will celebrate 60 years soon, and I was just wondering, do you feel yourself like being the center, and who do you see your next important competitor, if?
Well, on the first question, what should I say? Yes, I think we are the center in several respects. I mean, there are other very excellent centers, of course, all over the world, but in our particular field, in the research we are doing, and also in the way we are doing it, with so many nationalities working together, with the proactive attitude to get these people together, yes, we are the center, and the next competition is us. No, well, we have to take care to keep that standing. That's what I mean. The next competition is difficult to say. It depends where the governments want to make a global project. But to my mind, the best way to do a global project is where the experience is and where you have shown that you can do a global project.
Can I remind everybody that not only are there 3 physicists at the back of the room, but there are now 2 press releases. Some of you will only know of one, but there is now a second one has joined it spontaneously, we might say. And at this point, I am going to bring the press conference to a close and thank our speakers. And I'd ask you to let them get out of the room. It may be that you'll be able to squeeze one last question in on the way, but thank you very much indeed. And the next press conference is at 12:15. Thank you.